Okay, after the brief description about spring, now we are going to discuss about work energy. Again, work and energy. And till now we had discussed about only one particle. What would happen if we apply force to work on a particle? Now we are going to discuss what happen when there are many particles. Okay, this is the very important topic, and you should pay full attention on it. Okay, because in next chapter we learn about center of mass, etc. And in that case, uh, and at and in that chapter you will learn that if there is no external force, then momentum is going to conserve. Okay, so what will be the relation of external force and conservation of energy, etc.? We are going to learn about these things. Okay, guys, listen. uh, kinetic energy kinetic energy okay, kinetic energy kinetic energy change okay, by first work done work done by internal forces. Okay, internal, check the spelling, internal forces first thing. Okay, and it also change first thing. Second is it also change by work done. Okay, it also change by work uh, it also change by work done due to okay, due to external forces. Okay, guys, external forces. So work kinetic energy change first by work done by external forces, or internal forces work done by internal, this is internal forces, and it also change by work done due to external forces. Okay, okay, but what happened in case of momentum? What happened in the case of momentum? What happened? What happened in the case of momentum? Happen in the case of momentum. Case of momentum. Okay, you know, and due to it, this concept is become very important. Okay. What happened in the case of momentum? That momentum momentum change only by external forces. Okay, external forces. Okay, so due to this, people students confuse so many times that they think that uh, kinetic energy will also change only due to external force, and this is not happen. Okay, we'll see these things in examples when you solve the examples. Okay, so you should keep in mind. Okay, and if I am going to illustrate the things by theoretical present, then it become boring. Okay, so don't bother. We will see how internal forces change the kinetic energy. For example, the best thing is uh, thinking about friction. Thinking about friction. Let's suppose here this is this is a block. This is a block. Okay, and it is on ground, and here, and this is on, and this is on, uh, okay, this is mass m, and this is mass m by 2, let's suppose. And here the friction force here is mu. Here this is highly very high friction, very high, very high friction. Okay, high friction. So this is not going to move, not going to move, not going. Let's to keep the question simple, not going to move. Okay, now initially this is at velocity v. Okay guys, if I take these two as a system, okay, m, okay, a small m by 2 and m, if I take these two block as a system, you know so friction become internal forces, friction become internal forces. This means friction become internal forces, you know and in this case friction become internal forces, and in this case what happened, that mm, in this case, uh, the external force does not do any work, so but its momentum, its kinetic energy is going to change, because initial velocity is v. So after some time, let's suppose it will stop. So what is the change in moment, what is the change in energy? Half initial kinetic energy is half mv square. Okay, after some time, if this is not going to move and this block is very large, let's suppose very large, so after some time this block is going to stop. Okay, so what is the final kinetic energy? Kf is equal to 0. So what is the change in kinetic energy? Minus half mv square. So here there is no external force, I am just saying you, no external force, but kinetic energy has changed. Okay, so kinetic energy will change due to internal force as well as external force also. Okay, and in first look it may look slightly awkward for you, it's natural. This concept will be more clear when you learn about uh, momentum, when we learn the things in momentum. Okay, okay, now uh, let's introduce a new term called potential energy. And okay, potential energy is energy associated in particle due to its position. Energy associated in particle due to its position. Okay, okay guys, and due to its position. Okay, okay, and to understand the concept of potential energy, we have to introduce some new term, and these term are conservative force and non-conservative force. These are the very important term. Okay, these are the very important term, and we have to introduce the concept of conservative and non-conservative, uh, okay, forces. Okay, to uh, calculate these forces, you have to uh, sound knowledge of mathematics. Okay, in very complex situation, you have to calculate, but the good thing about this is, this complex situation is not in IIT syllabus. Okay, so okay, so uh, let's think about, go to new page. Here we are going to discuss about conservative and non-conservative forces and check how it is related to potential energy. Conservative force, a conservative force, conservative force. Okay guys, conservative force, this is the very important concept in, you know in mechanics. Conservative, the concept of conservative, non-conservative force, you know you know uh, the concept of potential, conservative, non-conservative force, electric field, these things are this concept, this topic is going is going to help you in many cases, and when you become an engineer, so many people had work on it. Okay, lot of people had work on it, and when you become an engineer, when you got a chance to study as engineer, then you learn about potential theory, etc. Okay, then you learn how important it is. Okay, so for the sake of the time, we are just going to discuss about some just simple definition and try to understand the things with some simple example. Okay, just simple example. And so many questions, so many book literature you will find on this topic, but and that literature and that topic is not in IIT's level, so we are not going to discuss about these things. But yeah, one thing I am uh, is important, that this topic, this topic is very important. Okay, okay, and people had expended a lot of time on this particular topic. Okay, particular topic. Okay, so let's start. Conservative forces. Conservative forces. Okay, conservative forces. Let's suppose a conservative forces. Let's suppose this is F dot dr. Okay, and when you integrate it in a loop, in a closed path, when you integrate in a closed path and this integration becomes zero, then we call such force as a conservative force. This is the very mathematical description of conservative force, but it is sufficient. Okay, okay, so first thing which is involved in conservative forces, first thing is closed loop. Closed loop. First thing is closed loop. Okay, first thing is closed loop. And okay, and second thing is, okay, if you move in a closed loop and if you integrate, if you try to find out this f dot dr in a closed loop, and if this value becomes zero, then your force F will be conservative, then F will be conservative. Okay, and no, and what is the meaning of this expression in term of physics is basically this term F dot dr, this is the work. Okay, this is the work, this is work done. So what is the conservative force? A conservative force is a force in which work done by that force on in a closed loop is zero. Okay, the conservative force is a force on which work done by that force in a closed loop is zero. Okay, if you look at this expression carefully, here work done by the force in a closed loop should be zero, then that force we will call conservative force. Okay guys, we will call conservative force. Okay, okay, let's check some common example. Some common example. Let's think about a common force, which is gravity, force by gravity. Okay, so in near the earth's surface. Okay, so here, if I throw a ball with velocity v, okay, and ball start reached at highest point and come down. Okay guys, so here this is the, what is a closed loop? Closed loop means if I started, if okay, if I reach to a initial point, to the point from where I had started, then we call it closed loop. Okay, what it mean that, if I started from here, okay, I go in this direction. Let's suppose I go in this direction and come back at this point again. is called closed loop. Again, another example is I started here. Okay, I go in this direction, then I go here, then I come back here. Okay, this is called closed loop. Okay, this is called closed loop. And a very interesting situation is rise when it becomes something like this. I go here, then come here and move like this, as like this is closed loop. But this is not simply connected. Okay, okay, this a simple looking thing is very complicated. Okay, so we not going to consider here this. Okay, we will consider such type of things. Okay, we will consider such type of things. Okay, so and we will consider such type of things. And and most simple is this. Okay, I go here and just return back. This is also a closed loop. Okay, so and this is the case, mg. This is the case of mg. Okay, so let's see what will happen. When I throw a ball, so let me draw the figure diagram of this ball. In air there is only one force, just neglect that air resistance. Okay, force due to air resistance. This is the mg. Okay, and what is the displacement? Displacement taking in this direction. Okay, so what is the work done here? Work done will be negative. Okay, this is the constant force, so work done will be minus mgh. Okay, now and when ball is moving in this direction, what is the work done? Is plus mgh. Okay, plus mg. So what is the net work done? Net work done is 0. Net work done is 0. Okay, so so this mg is a conservative force. Mg is conservative force. One force which we common experience in daily life is friction. Let's see, is friction is conservative force? Is friction a conservative force? Okay, let's suppose a ball. Okay, from here to here, this is the friction. Okay, here, and if maximum here, a ball move and reach here. Okay, so what is the work done by friction force? Okay, let me draw the figure diagram. It is moving in this direction, so the direction of friction force is like this. Okay, F, and displacement will this. So what is the work done by friction in this case? Minus Fx. Okay, now when it reached here, and let's suppose it come down again here by somewhere. So what is the work done by friction here again? Because friction force will be here and displacement is here, minus Fx. Okay, so here the friction force, again friction force is non-conservative force. Okay guys, so whatever whatever question people ask from you, you have to check it. Okay, and if you do not want to check, so then you have to do this, you have to follow this route. But this route is out of your syllabus. You cannot do it by your simple mathematical knowledge. Okay, which you taught in class 12th mathematics. Okay, so just forget about this. Okay, forget about this. And we have to choose the path like this. Okay, this is the simple path. Go here and return down in the same way, and you have to choose it. Okay, so this force is conservative and this force is non-conservative. Okay, in conservative force work done in closed loop should be 0, and non-conservative force work done in closed loop should not be 0. Okay, and it and this happen in whole region. Okay, this happen in whole region. Okay guys, now with this introduction, with little introduction of conservative force and non-conservative force, we are going to look into uh, uh, potential energy. Okay, what is the potential energy? Suppose, what is the potential energy? So we are able to discuss about potential energy, and this term are very important, okay, to understand the concept of potential energy. And you should read these things whatever I explain you today, like uh, energy conservation in multi-particle system, first thing, then conservative and non-conservative force in SC Verma. Very good book, and very good way explanation given in this book. Okay, you should read it. Okay, now we are going to discuss about potential energy. Okay, potential energy, what is the potential energy and how it arises. you know uh, potential energy is potential energy potential we are going to discuss about potential energy. Okay, okay, let's suppose a particle. The best way to explain the mathematics, the physics, is give up some simple example. Okay, let's suppose a particle is at this point and it is at this point, and okay, this particle O is at point O, this particle at point O, and we had an external agent. Let's suppose an external agent here. This is the external agent. Let's suppose this, and this external agent which apply a force F, which apply a force F has has moved has take the particle take the particle at 2 point, this is point A, to point B. Okay, to point B in such a way that that it is always in equilibrium, that it has no kinetic energy at any point. This particle has no kinetic energy at any point. Okay, then work done work done. Okay, let's suppose if this particle has take the part if this external agent which apply a force F take the particle from point A to point B, from point A to point B, uh, take the particle from point A to point B, then then it had to apply a force. Okay, force F. Okay, but if external agent will apply a force F, then how this particle will be equilibrium only by this force. Okay, there must be there must be a force. There must be a force. Okay, guys, there must be a force. Okay, and we call it we call it this force. We call it this force. You know, as field force, internal force, whatever you want to say. Field force, internal force. Okay, we call it field force, internal force, whatever you wanted to say. So okay, let me call it force, field. Okay, okay, field F, field. Okay, so there must be a force. There must be a force. Okay, which is in this system, okay, there must be a force which is in this system. So if external agent take the particle from A to B in such a way that it has no kinetic energy, and okay, no kinetic energy, and okay, in there is no kinetic energy in it, then work done by by this external agent is called potential energy. Okay, and this is the very important definition. The work done by, okay, and these things are going to help you when you learn about electric field, okay, when you learn about gravitational field. Okay, these definitions are very important. It is not, we are not going to use this definition, uh, we are not going to use this definition in work energy. Okay, definition of potential energy, conservative force, non-conservative force. But yeah, this definition are going to use when you learn about gravity and electrostats. Okay, so keep in mind. Okay, so work done by this external agent is called potential energy. Okay, and to keep this object in equilibrium, we always need a force. Okay, and that force is external force, and that force is, sorry, internal force must be in system which exert on this particle. Okay, guys, so if what is the work done by this external agent is called potential. And in on this in this particle, then there will be two force. In this particle, on this particle, there will be two force. One is work done work done by internal force internal force plus work done by external force. Okay, and this is zero. If this is zero and the internal force is conservative, conservative this internal force is conservative, then then what is the potential energy? Work done by external force, this is which is equal to potential energy, which is equal to minus of work done by internal force. So there is another definition of potential energy is minus of work done by internal force is called potential energy. Okay, whatever internal force will do work, yeah, in other way we could say that internal conservative force, whatever conservative force will do work on particle, then minus of that work will be potential energy. That minus of that work will be potential. Let me write this. Okay, and this is the very powerful definition, and it is very useful. Okay, let me write down. Potential energy is equal to minus of work done work done by internal internal conservative force. Okay, guys, conservative force. And very good explanation given in SC Verma. You should read this topic from SC Verma. Okay, you should read this topic from SC Verma. Very good description about these things given in that book. Okay, okay, now now we are going to mm, now we are going to discuss about uh, discuss about uh, conservation of energy. Now we are going to discuss about conservation of energy. Okay, and conservation of energy. So you know Listen here, conservation of energy. Okay, conservation of energy when there will be no external force. Okay, conservation of energy. These are the very important term. Conservation of energy. Conservation of energy. Conservation of energy. So when energy will conserve, so condition conservation of energy. Okay, and these are the theoretical things, but these are the very important. Okay, you should, oh, you should work on it. Okay, and very good discussion given in S.A. Burma. You should read that book. Okay, so conservation of energy. So first thing, uh, conservation of energy. Okay, first thing, all non-conservative, non-conservative, conservative, all non-conservative internal force, internal force, internal force, all non-conservative internal force work done. It may present. Okay, in physics every term is very important. Okay, work done, work done, zero. First, all non work done by all non-conservative internal forces should be zero. Okay, for conservation of energy, work done by all non-conservative internal forces, non-conservative internal forces should be zero. Okay, work done by all non-conservative internal forces should be zero. Guys, here in work energy theorem, the presence of force is not important. What is the important is the, that force doing work or not. Okay, is that force doing work or not is important. Okay, so when you try to understand the things by relating uh, momentum and energy conservation, then you see the difference. When momentum conservation, the action of force is important, if force is applied or not. Okay, and if force is present, then it will act on something. Okay, but in energy conservation, uh, the presence of forces is not important. Important is either they are doing work or not. For example, let's see a simple situation. you know okay, at this point giving example is not quite relevant. Okay, let me give you. Let's see, this is simple situation. This is this string. Okay, this is this string, and here, uh, and this is string. This is hanging from this support. Okay, this is ping. Okay, peg, and this is hanging from it. Okay, and you here you impart the velocity. Guys, here energy is conserved. Energy is conserved. Why energy is conserved? Because actually this is in air, and just forget that air has any resistance. Okay, here is frictionless. Let's suppose here is frictionless, it is in gravity. Here an external force is here. This is an external force. Okay, if I take spring as this whole as a system. Okay, and with gravity, then that pin, that peg, is a external force. But what is the good thing about this external force? No, so the presence of that external force will not allow to conserve the momentum. Okay, will not allow to conserve the momentum. But but that external force, the force. Okay, let me draw the what type of force I'm saying. Oh, okay, this is thing. This is T. So who has applied this T? T has applied by this peg. Okay, so the here the peg apply force on this whole system is string, or in our system is string, Bob and Earth. Okay, string Bob and Earth, but string Bob and Earth, but okay, this is string Bob and Earth in our system, but and on this system this peg is an external, the force by peg on this system is external. Okay, but luckily this external force is not doing any work. This external force is not doing any work. Okay, so guys, in this case momentum is energy is going to conserve, but momentum is not going to conserve because there is external force. Okay, so we have to think, we have to analyze the things. Okay, so if work done by all non-conservative, and here again this is a non-conservative force. Okay, so work done by all non-conservative internal forces. First thing, all work done by all non-conservative internal forces should be zero. First thing, and second thing is work done by external force. Work done by external force. External forces. All external forces should be zero. Then then kinetic energy plus potential energy. Kinetic energy plus potential energy is equal to constant. Then kinetic energy plus potential energy is going to be constant. Okay, kinetic energy plus potential energy is going to constant. Guys, why? Because uh, because what is the potential energy? Okay, so what is the change in kinetic energy? Let me write down the equation. There is only one type of force, which is internal force. Okay, there is only one type of force, which is internal force, and which is conservative. There is only one type of force, which is internal force, and which is conservative. So here let me write down, this is K final minus K initial. Okay, this should be equal to work done by conservative force. This should be equal to work done by conservative force if particle is moving from point 1 to point 8 1 to point B. Okay, guys. Okay, okay, and if you look at this, okay, by definition of potential, what is the potential energy? Minus of work done, minus of uh, change in potential energy. Okay, P2 minus P1 PE2. Okay, PE2 minus PE1. This should be equal to minus of F dot df. Okay, by definition of potential energy, minus of work done by internal conservative forces should be equal to minus of PE2 minus PE1. Okay, guys, so if we look at this expression carefully, what we get, K2 minus K1, this should be equal to minus of P2 minus P1. Okay, and this expression I can write it in this manner, K2 plus P2, this should be equal to K1 plus P1. Okay, this means kinetic energy plus potential energy, final kinetic energy plus final potential energy should be equal to initial kinetic energy plus initial kinetic energy. Okay, guys, so the sum of the potential energy plus kinetic energy is not going to change if work done by all external forces is zero. First thing, and second thing is work done by all internal non-conservative forces zero. Then energy will be conserved. Okay, so you should read these things from SC Verma. Okay, a very good explanation given in that book. Okay, okay, and it is quite confusing, for the beginners. Okay, beginners in mechanics. Okay, guys, so you should read these things from SC Verma. Okay, and whatever the things I have tell you is given in SC Verma. Okay, and it is very good summarizing concept. It nearly from 1 to 7 point written in the book. Okay, okay, and whatever I tell you, it is given in the book. You should read it. Okay,